Hello and welcome to another mini lesson about formal language theory. In the last several videos we've specified 3 different types of grammars, actually technically 4 different types of grammars. The unrestricted grammar, the context-sensitive grammar, the context-free grammar, and the regular grammar. And we've talked about how they form something called the Chomsky hierarchy because every regular grammar is also context-free, every context-free grammar is also context-sensitive, is also context-sensitive. Every context-sensitive grammar also fits into the unrestricted category, but not the other way around, right? An unrestricted grammar is not necessarily context-sensitive. A context-sensitive grammar is not necessarily context-free, and a context-free grammar is not necessarily a regular grammar. In this video, we're going to be talking about how we can change a regular grammar into a context-free grammar, and a context-free grammar can actually change into a context-sensitive grammar, and a context-sensitive grammar can change into an unrestricted grammar, though we won't actually do an example of that. We'll just assume that you can do that. Now, strictly speaking, a regular grammar is always a context-free grammar, because part of the definition of a context-free grammar is that a context-free grammar is that any regular grammar is a context-free grammar. That's part of the definition. But we wouldn't apply the word context-free to a given grammar if all the rules are regular. So let's talk about what we mean by this. So let's imagine that we have a language L, and that language is made up of any sequence of A's and B's in any order of any length. This was the original example that we used in the video about regular language to talk about how do we define a regular language. So we know that we can define this as a regular language. In the last time we talked about this language, though, we just talked about the rules of this language. We didn't actually talk about building the whole grammar. So before we do anything else, let's talk about what goes into the whole grammar of this regular language. So if we're defining this as a regular language, remember that every grammar contains a set VT of all of the terminal nodes, right? So these are your terminal symbols. In this case, the only symbols that we see showing up at the surface level are A and B. That's our only set of terminal nodes. Meanwhile, our set of non-terminals that we're going to use, which remember only show up in your rule set, right? They don't ever show up on the surface. Our set of non-terminals, we only have one non-terminal in this definition. We only have W, right? That's the only one we need. Then every grammar also has one of those non-terminals has to get called out as your start symbol, right? This basically means it goes at the top of each of your trees when you're building when you're building a language. And our start symbol for this regular language is going to be the only member of set N we have, the N that we have, which is W. So that's going to be our start symbol. And then we have our set of rules, which should look familiar to you, right? We have a W is made up of an A, or a W is made up of a B. A W can also be made up of an A followed by a W, or it can be made up of a B followed by a W. These conform to our definition of regular language, which says that a non-terminal can be made up of either a solo terminal or it can be made up of a solo terminal followed by a non-terminal, right? That's what regular language requires. So this is a regular language. Anytime you see a set of rules that fit the definition for regular language, we call it a regular language. Strictly speaking, we could also call it a context-free language. We could also call it a context-sensitive language. We could also call it an unrestricted language. But to do that doesn't fully describe what we're seeing here, which is that this really does fit the definition of the most restrictive form, right? So this fits the definition of the most restricted form. Let's talk about when we would start calling this grammar, right? This grammar, we would start calling it a context-free grammar, right? So what do we have to modify? We have to modify these rules. So how might we modify these rules in order to make them so that they no longer fit our strict definition of a regular language or a regular grammar, right? First thing we might do is we might just reverse the order of W and A here, right? So remember that we have to have X followed by B. We can't have B followed by X. And so even though this will generate our language just as effectively, right, we can have a W where the W, A, and then we have A, right? This will just as effectively generate our language, but it doesn't fit our definition of a regular language. It does fit our definition of a context-free language because we have only one non-terminal on the left side of each of these rules, right? So that's one way we can do it. We can redefine our rules just so that they look different, but they no longer suit the definition of a regular grammar. So we would call this a context-free grammar. But because we know that we can still define this using regular language, regular grammar rules, it still is a regular language. Because these rules are a lot simpler, are going to be simpler than these rules, right? They're going to be simpler to derive, right? And so we would rather call it regular, right? So this is a regular language because the language itself, remember this set, can be defined with a regular grammar. We choose to call this a regular language. But if this is the grammar that we're given for this language, which we can't call a regular grammar, we say it's a context-free grammar for a regular language. So what's another form of a context-free grammar that we could write for this regular language? Let's introduce a new non-terminal node, right? So here's our new non-terminal node, A. And this non-terminal node can only be made up of this little epsilon. So what does epsilon mean? When we're talking about formal languages, epsilon is an empty string. Is what we call this, and that basically means it's nothing. Right? You don't pronounce anything. There's nothing gets added when you add an empty string. We just use this as a variable so that we don't have to just write, nothing, right? Because that looks confusing, right? So this just stands for nothingness, right? So how might we modify our rules now that we have this nothingness added, right? We still have the same two rules that we had here. We still have this rule essentially, except that you're allowed to add nothing on the side. Right, so this rule no longer fits our definition of a regular grammar, and because you've got too much stuff on the right side of your rule, even though you're not actually adding anything, right? So this is a context-free grammar for a regular language. This is another way that we might rewrite our grammar in order to describe this regular language, right? Let's talk about how we might make this context-sensitive. Right, we're basically going to do the same thing. Whoops, we didn't add these in. Sorry about that. That's what these are supposed to be, right? But we're basically going to do the same thing, except now we're making the left side so that it also contains some wacky stuff, right? So these are no longer rules that can be called context-free, right? This is a context-sensitive rule, even though it's not really adding anything to your language. It is changing the way our rule set looks, and so your grammar is going to be a context-sensitive grammar. Now notice that we have chosen to call this a regular language, even if it's described using a context-sensitive grammar, because the regular language is the simplest way to describe it. This will require the least complicated set of rules, and so we call this a regular language. So simpler rules are in this direction, right? As you get more complicated rules, you can start to make more wacky-looking languages, right? So we call this, the more wacky-looking your language, the languages that you can describe, the more powerful your grammar is, right? So you have more complicated rules, but you can make a more complicated language with that, right? So in this direction on the Chomsky hierarchy, or moving down in the Chomsky hierarchy, you're getting simpler and simpler rules, but you can't make languages that are as interesting. They're less powerful, right? So if you've got simple rules, you can't do as much with them, right? And you might need more rules maybe to account for something. But as you move up, you can make more and more complicated languages because your rules are more and more complicated. But also you have to deal with the fact that you have more complicated rules. And this also means, in terms of, stuff that you would be dealing with in computer science, that you're going to have a smarter and smarter computer to deal with any of these more complicated grammars, right? So this is a dumb computer can deal with this. You have to have a really smart computer to deal with languages like this, right? So more power equals more thinking, right? This is more powerful, but you have to do more thinking. This is less powerful, you have to do less thinking. So that's what the point of this Chomsky hierarchy is, and we'll talk over the next several videos about how to determine when you receive a grammar that looks like this, whether maybe we could model this more simply, requiring less thinking, right, in a form that requires less thinking, whether we could rewrite this in a way that requires less thinking. So moving up the Chomsky hierarchy is always easy. Moving down, whether or not you can move down is going to be the question that we're asking a lot, right? So in some cases you receive a context-sensitive grammar for a regular language, and in other cases you receive a context-sensitive grammar for a context-sensitive language, right? And we want to know how much less thinking we can do given one of these grammars.